What's going on, guys? Welcome back to another video. In this one, we're going to do Leetcode 94 binary tree in-order traversal. Okay, so given a binary tree, return the in-order traversal of its nodes values. In order being left, node, right. Okay, so we can see the output here is 1, 3, 2. We went 1, there's no left, so we come back to the 1. Then we check the right. The right has a left, so we put the 2 in. Then we check the node and we add it. Okay, so 1, 3, 2. Follow-up recursive solution is trivial. Could you do it iteratively? Okay, Leetcode, that feels a bit like a personal attack. So we're going to do it both ways. Okay, let's start with the recursive solution because generally sort of tree traversal problems lend themselves pretty easily to recursive solutions. So we'll create an output that's going to hold the stuff that we're going to hold at the end. And we can do this with a little helper function. So this actually is this tail call recursive? I think so. Anyway, we're going to create a little helper function. We're going to say pass a node to it, which when we first call it is going to be the root. And if we're going to say if that node doesn't exist, we're just going to return up the stack. So cool. Otherwise, we can just call itself with some values. So we're going to call itself with the left node, and then we're going to add to the output array the center node, and then we're going to call it on the right. Helper node.right. Then we're done, actually. That's pretty much it. And we can actually say helper pass in the root, which is the first argument, to the main function, and return the output. So this should work. Let's try that. Tree node. Oh, I always do this. So we forgot to, we're actually passing in the full node here, not just the value. So let's do that. Okay, cool. Recursive solution works. Now, they want us to do the less trivial solution, which is to do it iteratively. So let's do that. So what we're going to do to solve this is use a stack. Okay, and what we can do is keep our we're going to have an output array, just like we did in the recursive solution, and a stack. And we're going to keep checking if there's stuff in our stack. So while there is stuff in our stack, or the root does exist, we can then check if we can add the root to the stack and then sort of reassign the value of root to the left item. And if there is no root, it means we're going to take something from the stack and add it to the output and then assign the value of root to the right item. Okay? So that may be a little bit hard to follow. Let's actually just try to do this in code. It's a lot more intuitive than just talking about it. So I'm going to create a stack and an output array. Okay. Then I'm going to say while stack or root. What we can then do here is check if the root exists and append to the stack. Let's just add that in there. We're going to add 1 in this case, and then reassign our root to be the left. So there is no left here, right? Okay. So the next time around, this isn't even going to exist because it's null. So we're going to have to hit this case. We're going to create a temporary variable here to hold what we pop out of the stack, which if you remember we added 1, so we're going to pop that out. So we're going to say, let's just call it like holder, placeholder, stack.pop. Okay, then we can add that holder to our output so that it shows up. It'll be 1. And again, let's make sure we do the value, not the whole tree. And then root is going to be equals to the right value. Okay, and then at the end, now our stack is going to be totally flushed, and we will have added everything to the output, and we can just return the output. Now in Python, you could probably do this with a deck, right? But I think since we're adding to the end and popping from the end, it's still linear time. So, excuse me, not linear time, constant time. All right, it's O of 1. So let's try to submit that first of all before so make sure it works. Cool, very slow. Again, these interpreted language runtimes, I don't know if I trust them, but 14%, oh my god, okay. Terrible. One more time, we're going to give it one more. Now maybe I'll do this in Scala, because just terrible. All right, we're fired. We couldn't make this faster. Anyway, here we had to traverse the whole tree, right? So, yeah, it's going to be a linear time complexity. That's not what this represents. This is just how long it took to run it. But if you're asked to tell somebody what the sort of asymptotic runtime of it is, you'll just say linear, right? Because we had to hit every item and add it to the stack. And yeah, and we did have to use extra data structures. So it's not a constant a constant space algorithm either. All right, guys. I hope that made sense. Go ahead and try this by hand and see if you're able to reason about this. Again, I usually do these in a recursive way just because it's a lot simpler to reason about, and you don't need to use a stack. But either way works, and you can actually traverse a tree in several other orders by doing something like this. So maybe we'll do that in the next one. Thanks guys for watching. Catch you in the next one. Bye.